So now we've talked about examples where two objects collide and stick together. And once they stick together, then we have what is referred to as inelastic collisions. All right. Let's talk a little bit more about elastic collisions. So elastic collisions, momentum is conserved. So any collision, as long as there's no outside net force, momentum is going to be conserved. But in order to call it elastic, kinetic energy also needs to be conserved. Now, there's nothing in nature that says kinetic energy has to be conserved, but if kinetic energy is conserved, then it's an elastic collision. If kinetic energy is not conserved, it's considered inelastic. Now, really, elastic and inelastic is on a range of whether kinetic energy is conserved or not conserved. Perfectly elastic collisions where you have all the kinetic energy conserved. Now, in real life, you never have all kinetic energy conserved. And then if you have two objects stick together, that's referred to as perfectly inelastic. So you got one end where you got kinetic energy conserved, the other end where you have perfectly inelastic, and then you got stuff in between where some kinetic energy is conserved, but not all of it. Now, if it's considered elastic, mathematically kinetic energy is conserved, but conceptually to look at a scenario and determine whether it's elastic, as you would see the objects bounce off of each other. And the more bouncy the situation is, the more kinetic energy is going to be conserved. When the two objects collide and stick together, that's more of an inelastic collision. So if you want to conceptually look at what an elastic and inelastic collision are, elastic is going to be bouncy, where inelastic is going to be sticking together. So we took a look at an inelastic collision where two objects stick together. So let's suppose the second object right here has an initial velocity back in the other direction. And then when they stick together, they're going to have a final velocity. Now, we don't really know what direction the final velocity is going to be because both objects have a velocity initially, and then at the end, it could be moving to the right or could be moving to the left. Now, what determines what direction it's going to be moving is which object actually had more momentum initially. And it's not the one with more mass, but it's the one with more mass times velocity. So before the collision, if you look before the collision, the two objects have momentum, mass 1 times initial velocity 1, mass 2 initial velocity 2, and then afterwards, the two objects you can basically treat as one object. When two objects stick together, you can effectively treat it as one and then multiply by the final velocity. Now, if you want to treat them as separate objects mathematically, you still get the same thing, but simplify it a little bit, you can treat them both as one, add them together, and then multiply by the velocity. So before you got your mass 1, initial velocity 1 plus mass 2, and notice the initial velocity 2 is in the negative direction. All right, so the negative direction is going to be moving that way, so we give it a negative in the equation. All right, afterwards, both of them again stuck together, are going to be multiplied by the final velocity. So to get the equation for the final velocity, basically you take the entire momentum before and then divide by the total mass, and that gives you your final velocity of the objects. All right, in an inelastic collision, if momentum is conserved, and which of the following statements is true about kinetic energy? I'll give you a second to try this. All right, so in inelastic collisions, kinetic energy is not conserved, so definitely not A. Now, is kinetic energy gained or lost? All right, so in most scenarios, especially if we call it an inelastic collision, the energy is going to be lost. Now, what about kinetic energy being gained? Is that a possibility? Usually when kinetic energy is gained, you basically it's a third type of collision. So you got elastic, inelastic, and the third type of collision is generally what we call like an explosion. An explosion is where initially maybe nothing is moving, but then there's something in between that causes them to push away from each other really quick. In labs, we'll have a spring-loaded cart where we release the spring and it pushes against the carts, and then you move away. That's where kinetic energy is going to be gained because the spring does work on each of the carts, and doing work creates kinetic energy. All right, but for inelastic collisions, kinetic energy is going to be lost. All right, so this question says two objects collide and stick together. Kinetic energy, what? Go ahead and take a second to figure this out. All right, hopefully you remember when objects stick together, we call that an inelastic collision, and inelastic collisions where kinetic energy is not conserved, so it's definitely not conserved. All right, so here we have an elastic collision where two objects are moving towards each other and they bounce off of each other. Now, I could go through the entire scenario of how we come up with these two equations I'm going to show you. All right, so both of these equations basically predict what the final velocity is going to be for each object. Now, you can see it's in terms of the masses of the objects as well as the initial velocity of both objects. Now, these equations come out because basically what you do is you take conservation of momentum and conservation of kinetic energy, combine the equations, you eventually get to these. So it's a lot of work in order to get to these points. But basically, I want to look through these scenarios and kind of see what happens in specific instances. So let's start with one instance. For example, let's say that the two masses are the same mass. Let's say that they're the same amount. Both of them are 1 kilogram, for example. So what's going to happen with the objects when they bounce off of each other? What happens if they bounce off of each other? All right, so if both of them have the same mass, you see right here that this term is going to be mass A minus mass B. That's going to, with the same mass, this is going to be 0. All right, so the final velocity of A is going to have nothing to do with the initial velocity of A, which is kind of weird to think about. But if you look over here, the second term, you got mass A, mass B. That's 2 times, because they're the same, and then mass A and mass B being the same will cancel with mass B up here, and you get 2 divided by 2, which is a ratio of 1. So effectively, you get 1 times the initial velocity of B. So the final velocity of A, if the two masses are the same and they bounce off of each other elastically, then the final velocity of A will take on the initial velocity from B. All right, so what about B? What happens to the final velocity of B? Well, again, both of them are the same, so you got the denominator here where these two terms are the same, so it's going to be basically like 2x, and then at the top we got 2x, so that we get a ratio of 1, so we get an initial velocity of A times 1. And then over here you got mass B and mass A being equal, so that's going to be 0. So again, the initial velocity of B is going to go away. So effectively, the final velocity of B is going to be equal to the initial velocity of A. All right, so that's mathematically, but conceptually, what does that mean? Essentially, what we have is we have the two objects as they're moving towards each other, and they bounce elastically. They will literally switch their velocities. So the velocity of A will now be transferred over to B, and the velocity of B will be transferred over to A. So if A was originally moving at 3 meters per second, then B afterward is going to be moving at 3 meters per second. If B was moving at -2 meters per second, then afterward, A is going to be moving at -2 meters per second. They switch their velocities. All right, so what about another scenario? Let's suppose that one mass is really, really massive and the other mass is very, very tiny. What happens there? Okay, so let's say A is really massive. A is the really massive object. All right, so let's look at this term. A being really massive and B being not so massive at all. Effectively, A minus B gives you A. It's like saying 10,000 divided or minus 1. What is that going to be? Well, it's 9,999, but it's essentially still 10,000. What about the denominator? All right, 10,000 plus 1. That's 10,001. That's essentially still 10,000 though. So what you have is when A is extremely more massive than B, then you get a ratio here of about 1. Now what about over here? Well, you get mass B, which is really, really small compared to mass A. So that means you have a really tiny number in the numerator, and the denominator, you have a really big number. So when you got a really small number divided by a really, really big number, essentially that is very, very tiny, almost 0. Okay, and the bigger the difference between the masses, the closer that is going to be 0. So we effectively are going to have a initial velocity of 0 here multiplied, and then we have the final velocity of A. The initial velocity of B has 0 effect on it, so it's going to be equal to the initial velocity of A. So basically, when two objects collide and they bounce off of each other, if one is extremely massive, then its final velocity will be equal to its initial velocity. Hopefully that kind of makes sense. You know, you get an object that's really massive and another object just kind of bounces off of it, well, the other object is really not going to go anywhere. It's just going to continue going as fast as it was before. Okay, so what about the little object? What about the small object? All right, well, let's look at this term. So here we have mass A, 2 times mass A, divided by mass A plus mass B. Now again, we said that mass A and mass B added together really is not different than mass A. It's such a small difference that's effectively equal to mass A. So mass A cancels from the numerator denominator. You get 2 left over for this ratio. All right, so what about here? Well, mass B minus mass A, essentially that's going to still be negative mass A, and then we get mass A plus mass B, so we get negative A over mass A, so it's negative velocity of B. Okay, so we get 2 times the velocity of A minus the velocity of B. So essentially, the initial velocity of B is going to go in the other direction, and we're going to add twice the velocity of whatever A was. Okay, so again, the initial velocity of B is going to be negative. So let's say mass A wasn't moving. Let's say it was just sitting there. So mass B is going to come toward it with some velocity, and it's going to bounce back and go the opposite direction with some velocity. But if mass A does have a velocity, let's say it's a big medicine ball that's really bouncy, and a small little ball bounces off of it, well, that small ball is going to have its initial velocity away plus twice of the velocity of A. All right, so that's two major scenarios that you get with this, where you get one object that where the two objects are going to be the same mass, and when they're the same mass, they basically switch their velocities. If one is exceedingly more massive than the other, then the one that's exceedingly more massive, its velocity is not going to change. The one that's not very massive at all is going to gain its velocity back in the other direction, plus twice of the velocity of the big mass. All right, so let's go through a couple scenarios with this. All right, so as we mentioned before, B is at rest. So what happens to the mass of A? All right, so we talked about this. Then effectively the 0 goes away here because the mass B with initial velocity is 0, so that means initial velocity of both of these is going to be 0. So if you take these two right here, if they have the same mass, then the initial velocity of A, or the final velocity of A, is going to be 0, because with the same mass it's going to be 0. The final velocity of B is going to be equal to the initial velocity of A, because it takes on, basically they switch their two velocities. Next scenario, let's say that the masses are going to be equal to the initial velocities B, of B is 0. Then this is what I mentioned before, right? So A is going to take on the velocity of 0, because that's what B had initially. And then B, its final velocity, is going to be equal to what the initial velocity of A was. All right, in elastic collision, if momentum is conserved, then which of the following statements is true about kinetic energy? Go ahead and give this a shot. Okay, so as long as it's a collision where momentum is conserved, we assume no outside net forces. If it's elastic, that means that kinetic energy must be conserved. All right, that's more so kinetic energy is conserved and we can call it elastic. We don't just say it's elastic and then all of a sudden nature makes kinetic energy conserved. We have to see that kinetic energy is conserved before we can call it elastic. Next question, when is kinetic energy conserved? Go ahead and try this. All right, so definitely not all collisions, definitely not inelastic collisions. Collisions which they do not stick together, that's not necessarily true, but if they stick together, they're definitely not conserved kinetic energy. So only in elastic collisions is kinetic energy conserved. All right, it says when a light beach ball rolling at a speed of 6 meters per second collides into a heavy exercise ball that's at rest, the beach ball's speed after the collision will be approximately what? All right, so this is that scenario I was talking about where you have one that's extremely massive and the other that's very, very light. So if you remember, the beach ball, or I'm sorry, the exercise ball being extremely massive, its velocity essentially is not going to change, so it's going to stay at 0. But what happens to the beach ball as it bounces off? Well, what happens is it's going to go in the opposite direction, and then it's going to add 2 times the velocity of the heavier ball. Well, the heavier ball is not moving, so you don't have to worry about that. So basically, the beach ball is going to go in the opposite direction. So it's going to be 6 meters per second in the opposite direction. All right, 2 billiard balls of equal mass undergo perfectly elastic collision, head-on collision. If one has a speed of 2 meters per second, the other has a speed of 3 meters per second in the opposite direction, what will their speeds be after the collision? Go ahead and give this a shot. All right, so just as we mentioned before, two objects that collide elastically, if they have the same mass, they literally switch their two velocities. So the velocity of the first billiard ball that was moving at 2 meters per second is now going to be negative 3 meters per second. And the velocity of the second billiard ball that was moving at negative 3 meters per second is now going to be equal to the billiard ball, or the first billiard ball, which is 2 meters per second.